Hi everyone and welcome back to chemistry. This is Mrs. Hutchinson and today we're going to continue our discussion on the history of the atom, and we're really going to dive into that topic that I've been telling you we're going to dive into for a while, isotopes. So really, before we get into what isotopes are, let's actually break down the term isotope. So in English, iso means the same, so an isotope means that we're talking about atoms of the same element. The definition of an isotope, however, is that they're atoms of the same element that differ in numbers of neutrons. So this first bullet point happens to give us the definition of an isotope. So atoms of the same element that have different numbers of neutrons. They happen to have the same number of protons and the same number of electrons, though. Remember, number of protons never changes. So things that I want you to remember here, we've discussed ions before, and now we're discussing isotopes. So what's the difference between an isotope and an ion? An ion, they differ in numbers of electrons. So ions either gain or lose electrons. Isotopes differ in neutrons. So that's where the difference between an ion and an isotope really lies. Now, isotopes, they differ only in mass and not their chemical properties. And here's why. Because isotopes differ in numbers of neutrons, that means that if an atom has one extra neutron than another one, then it's going to have 1 AMU higher of an atomic mass because it's got one more particle, one more neutron to it. But their chemical properties, however, as we find out later on in chemistry, chemical properties are determined by the numbers of electrons. So since isotopes have the same numbers of electrons, that means their chemical properties are going to be the same or very similar. And isotopes also, if you take a look on the reference table, they're kind of given to us in the atomic masses on the reference table, on the periodic table. If you take a look at the atomic masses, they're not whole numbers. But here's why. Because the atomic masses are actually the average. And when we get to it for our next video, we're going to talk about the weighted average of all of the naturally occurring isotopes. So the key word here would be naturally occurring. Averages are rarely whole numbers, so that's why our atomic masses are not whole numbers. And we'll see that with our next video, how you can calculate that average. So, taking a look at our examples of isotopes. So, there are 3 natural isotopes of hydrogen. And those isotopes are known as protium, deuterium, and tritium. The only difference between these 3 atoms of hydrogen would be the fact that they all have different numbers of neutrons. Now, protium is actually a proton, but what I'm going to do is I'm going to show you isotope symbols of each one of these different isotopes of hydrogen. So, taking a look at protium, the first thing that we want to write would be our atomic symbol of hydrogen. The next thing is let's write the atomic number of hydrogen. Remember, the atomic number is our number of protons that exists in that particular atom. And the number of protons never changes. So number of protons never changes. So that means that each one of these isotopes is going to contain the same atomic number for hydrogen. What is going to change would be our mass number up top here. In fact, let me write that in a different color. So it's our mass number up here. That mass number, if you remember, represents our number of protons plus neutrons. So, since our number of neutrons changes, our mass number will also change. What we can then use would be, we can use our mass number and our atomic number to determine the number of protons and neutrons that exist within this particular isotope of hydrogen. So, if we had to look over here, how many protons do we have? Well, our protons are told to us by our atomic number. We have 1 for our atomic number, therefore we have 1 proton. Our mass number can be used to determine our total number of neutrons. Remember, to determine the total number of neutrons, you're going to take the difference between our mass number and our atomic number. And that's going to leave us with our number of neutrons. So, in this particular instance, we've got 1 minus 1. It's going to give us our total number of neutrons, and we've got 0 neutrons for protium. Another way of writing this would be H-1. Okay, so we've got 2 symbols we can use. This one here and H-1. So let's write another one for deuterium. So, deuterium. We write our atomic symbol. We write our atomic number. Remember, our atomic number never changes. But deuterium is actually used for heavy water. So, again, remember the mass number changes. So that's something that I would have to tell you, would be what mass number we're dealing with. So we now have 2 for our mass number. So let's take a look at how many protons we have. Well, our atomic number remains the same, so we've got 1 proton. And our number of neutrons would be 2 minus 1, giving us 1 neutron. And another symbol that we would use would be H-2. Last but not least, let's draw our symbol for tritium. Tritium sounds like 3, so yeah, it is. So our mass number in this instance will actually wind up being 3. Our atomic number, remember, always remains the same. Our mass number here is 3. So if we had to determine the number of protons, we've got 1 proton because our atomic number is still 1. Our number of neutrons, however, is now 3 minus 1, so we have 2 for neutrons. And another symbol that we would use would be H-3. Okay. So what makes these all isotopes would be the fact that they differ in mass numbers, but they also are going to differ in numbers of neutrons, which is what causes their mass numbers to change. So now, let's figure out how many neutrons exist in this particular element. Now, of course, because I am not exactly computer savvy and very good with computers, one would say, is that I couldn't figure out how to, write these on Word. So I'm just going to write them in. So in your packet, go ahead and write these numbers in as well on top. So those will have to be given to you. So question is how many neutrons are in the following isotopes of this particular element, and then what is the name of this particular element? So things that we need to recognize: our bottom number tells us our atomic number, so that tells us our number of protons, and our top number is our mass number, and that's going to tell us our number of protons plus neutrons. So, again, to determine the total number of neutrons, you want to take our mass number and subtract our atomic number. to get our number of neutrons. So, we've got 15 minus 8, hopefully gives us 7 neutrons. Here we have 16 minus 8, 8 neutrons. And 17 minus 8 gives us 9 neutrons. So these are different isotopes of the same element because they have the same atomic number, but they have differing numbers of neutrons and differing mass numbers. The name of this element, so if you look up an element with the atomic number of 8, you'll notice that you're looking at oxygen on your periodic table. So now we have a worksheet on isotopes. What I want you to do is fill out the first question, define isotopes in terms of subatomic particles. What exactly do isotopes of the same element differ in? And then for the following isotopes, determine the number of protons and neutrons that exist based on their symbols. So if we take a look at this particular symbol here, so CS-133, cesium-133. Well, 133 is our mass number. That's our number of protons and neutrons. Cesium, if you look it up on your reference table, so cesium's atomic number that I just looked up is 55. So, that atomic number tells us our number of protons. So, we can use those numbers to help us determine our number of protons in a cesium-133 atom, and our number of neutrons in a cesium-133 atom. So, our number of protons always going to be equal to our atomic number for every single atom. Darn it, where'd it go? Here we go. So, in our case, we have 55 protons, and our number of neutrons winds up being 133 minus 55, which is going to give us a number of neutrons of 78. So 78 neutrons for cesium. Okay, so do the rest of this worksheet. And if you have any questions, you can ask me in class, and I will see you for our next video.